Good afternoon, everyone. On behalf of Department of Electronics and Communication Engineering, R.M.D Engineering College, and my own behalf, I welcome all the participants for the Day 6 of AICTE-sponsored FDP on Next-Gen VLSI and Semiconductor Systems, Integrating Machine Learning for Intelligent Design Automation. It's my privilege to welcome our eminent speaker of the session, 11, Mr. Shivaprasad, Executive Manager, Entuple Technologies, Bangalore, to deliver the session on the topic Next Gen Automation, the Role of AI Accelerators. My heartfelt gratitude for accepting our invitation to share your expertise among us amidst your busy schedule, sir. Thank you so much, sir. And now I invite Ms. Srinidhi to introduce the speaker. Over to Srinidhi.
Good, eve- Good afternoon, everyone. Well, it's my pleasure to introduce our distinguished speaker, Mr. Shivaprasad B K, who currently serves as an execution manager at Entuple Technologies, Bengaluru. Mr. Shivaprasad completed his MTech in VLSI Design and Testing from BV Bhumadri College of Engineering and Technology, Hubli, in 2014, and holds a bachelor's degree in Electronic and Communication Engineering from SJM Institute of Technology, Chitradurga. He brings with him over 9 years of experience in the VLSI industry with strong expertise across asset design and verification, full custom and mixed signal design tool flows using Cadence EDA. He also a certified trainer recognized by Cadence with a digital badge for excellence in languages and methodologies. Earlier in his career, Mr. Shivaprasad worked as an intern at ISRO Bangalore, where he developed a floating point hardware accelerator to for the altitude and orbit control system in spacecrafts, a truly remarkable contribution. Beyond his technical expertise, he is a lifetime member of ISTE and was honored with the Entuple Auxilium Award in 2024 for Best Technical Support Management. We are delighted to have him with us today to share his insights on AI accelerators and their pivotal role in shaping next generation automation. I warmly welcome you, sir. The session is over to you. Thank you so much, sir.
Thank you, ma'am. Thank you for kind introduction. Uh, yeah, let me share my screen. Could you please confirm, ma'am?
Yes, sir, it's visible.
Great. Let me take presentation mode. Yeah, very good afternoon, all. First of all, thank you for R.M.D College of Engineering for giving this opportunity. Hopefully, for this entire week, you had a very good sessions. And today, uh, we are going to see couple of minutes. Next means the topic going to see on the next generation automation, the role of AI accelerators. So the topic is very relevant to present industry, and this is very much very insightful. And the topic, the form of the topic, if we try to decode and we try to be get the as much as and uh, just before starting our session, small housekeeping notes. Here my network little small means a little fluctuating. If any network issues comes, just kindly hold on. I will be connected at within minutes and seconds. So, and the next, if you have any questions when we are discussing the slides, free feel to drop so that we can take a flag end of the session as a discussion. Yeah, with these notes, yeah. So if we see our topic here, the automation and here the automation and acceleration. Okay, so automation has been there for the over the years. Like we have been automating, even if all of if I means all our participants aware of, like when we are implementing a chip designing, the simple example earlier, we used to have small layout with the hands of transistors. Now we are automation, how many billions and trillions of transistors in a single IC. So the automation and also Moore's law, so they have been so much, like it's a expectations, like a trend to be continue, and accordingly the process, the workflow or delivering the chip performance and the workload also it is going to be enhancing. So with this note, they have been doing the automation of the workflows, like in the steps. If you see her simulation point of view, synthesis point of view, in synthesis you have multiple corners, multiple modes and multiple corners, like kind of all. So, and there is a best example we can say that like TCL commands and all, so it will scripting help us to be process entire flows. So when another terminology here, if you see acceleration, so acceleration is something like we have existed work but we need to be little more enhanced. So in this session I'll try to correlate in the one small snapshot of the tool flow, as well as we published some of the papers in this acceleration related, and we will hopefully will see that case study if time allows. Now, before going to the automation, we'll see accelerators. We can, in the place of AI, we can think about hardware accelerators. So hardware accelerators, like the best example in our hand, we have the mobile. Earlier, small operations. That's why you have single core one mobile processor there. Now, presently, if you take Apple or any kind of phones, you can see there are so many processors are there. Like a graphical processing separate task, it will handle by GPU, and the neural network like NPU is there, and the IM image processing in it like IMP, and video processing in it like a VPU. So there are a lot of things. Means a different task for different. Okay, so if you think about what is really meant accelerator, just think like a highway, a single line highway. You have limited possibility, and you can have to be processed serially. You have to process all the tasks serially. When you come to the multi-lane highway, so you have multiple lines around the eight way or six way, so eight different or six different tasks you can be handled. So that means workload more increases, and you have used throughput, and you have more capabilities. So single line we can call it as a conventional way, where you have the multiple lane we call it as a accelerator or accelerating our work. So now presently the AI everywhere in a part of our life, but it is not the new terminology. It has been already there 90s, 80s and 70s itself. Now why it became very nowadays become buzzword, and everywhere it is impacting, and that it's showing the results and all. The reason, like earlier they used to have algorithmic level, not much hardware support. And the best example, if you take NVIDIA kind of companies, they use it to be develop a graphic processing unit, GPUs, that for 3D and gaming purpose. Fortunately, by their luck, the AI related tasks we need mainly learning, training, and then deploying some kind of, these are the tasks main inherently. All are basically, AI related, deep learning, machine learning. Core concept are like a multipliers and linear algebra, and also conventional convolution, mathematical, compute intensive tasks are there. So this GPU is very suitable for this AI related application. That's the reason the company, initially it was like a very medium scale company. Now it become all the way top best and 5 trillion. So they have been mainly their market for AI related hardware support. So these are now data centers, from our smartphones to data centers, you need AI related solutions. The same way you need accelerators. So these hardware accelerators, deep neural network purpose, so mathematical support and all. So we need support wise, as well as there are not like a conventional architectures not work, and you need also have challenges accompany. And we're going to see what are the trends set for us when we go down the line. So this is a problem statement we can say for our present topic. So you can see from the 12, 2012 to, let me take pen. It will easy for to note. Yeah. Yeah. So, well, if you see here in the 2012, we have computation wise, and then you can see the this one AI needs. This one AI needs is very low in 2012, and then this line you can see amber line is a like a CPU. So you have solutions for this computation. So here I this is high computation and low computation. So the from year to year, if you see this computation is increasing, and 12 to, so this AI going to be exponentially increasing like this. Okay, now we are here, and then you have conventional computation purpose. We have CPU performance. So this is the CPU study line. Okay, so this study line is some extent it may be 2015 till means maybe you can think about 20 till 2015. I mean exactly 10 years back. Maybe some of the CPUs going to be helpful for our AI needs. But after 2015 onwards, now all we required some specialized hardware. As we best example, all we are aware about FPGA, right? FPGA hardware is a field programmable gate array. So you can be multiplier. There is a separate unit is called mac unit, mac. Okay, so if let assume that any DSP application, you need to do some two kinds of operation. One is the multiplier, another one is the addition. So if you use multiplier and addition operation separately with the different hardware or different logic, your power and performance and PPA, we call it as a PPA, it is going to be different. Whereas the same kind of operations, if you are use with the Mac unit, your perform this is going to be very optimized. So what it is here, this is the conventional way, traditional or conventional way, whereas this one is a specialized hardware or specific application, DSP application purpose, they have designed this one. So if we can correlate like this. So here AI related especially need hardware, thus the demand is increasing. So yeah, so it now see this, we need to address this gap. Okay, to need the address need to this gap, that's why companies are creating AI means enabled or AI support hardwares. So majorly AI related applications and operations are compute intensive task of multiple multipliers. And there is also like this kind of FPGA architectures, you can also find there is a specialized hardware called DSP15. So DSP15 is a specialized multiplier, very optimized in terms of power and performance. This is also specialized hardware which give the better results when you go for multiplication instead of conventional way. So this kind of applications we can enable, and some companies, majorly many of the companies now presently, Nvidia, Qualcomm, Broadcom, everybody is now targeting for AI related support hardware development in a chip. So best example, M4 M4 chip, Apple M4 chip, if you are analyze, you can have this GPU, TPU, NPU, means GPU graphic processing in it, and then neural processing in it, NPU, and video VPU video processing in it, IMP image processing in it. All are four in this one chip, one silicon. So earlier, AI means only algorithm. Now, AI means silicon support also. You need a silicon which support your AI needs. That's the major. So, if we understand this, the slide and the problem statement. Then remaining things are related to the your information only. Remaining things like what are the things have been there existed for the advance. Okay, yeah. Let me take. Yeah. So now come to the slide. Like what is really acceleration? So as we have analyzed. So here is the specialized hardware. You can see. So specialized hardware can perform specific functions. So the question is whether the general purpose CPU, whether it is not do this on or will do or not. So it's like we can have the question like this. So the thing is like CPUs are good at it. We can say it is a good at multiple tasks, but it is not best in a one task. We used to have saying, right, in English, there is a jack of all trade but master in none. So CPU can be good at multiple tasks, but it is not excellent in one task. So that's where we have the gap for the CPUs. Now people have been doing some experimentation with the CPU with the multiple threading or multiple core, multiple threading. So that where some extent they are trying to be support this AI application, but ultimately there is a power performance and area when it is comes, we need some different architectures. But CPUs have kind of architecture. You have memory communicate with the separate, and then computing task is separate. So where Newman architectures and different architectures we're going to see in the upcoming slides, and we're going to see the architecture type. What are the different architecture helpful for AI acceleration or hardware acceleration? So, and the AI related, we are combining the CPU capabilities with the graphical processing unit and application specific IC. Like FPGAs prototyping purpose we uses. Once we prototyping done, we go for our application specific hardware. So these all capabilities we are creating, and then best example we can see like a graphical processing unit. You can play the 8K resolution and 4K resolution. The best example we can see, right, in mobile. If you take in our mobile, you have the hardware video codecs are there, software video codec. So video codec means encoder decoder. So encoder means camera, decoder means it displays in your mobile screen. Okay. So codec, both we call it encoder decoder as a codec. So here software codec, if you are enable, that means CPU, your mobile CPU will be decode your encode your 8K 4K resolution. So just think one 8K resolution video with the CPU. Okay, within few minutes your battery going to be drained. So that means it is a power intensive. Whereas the same, you in your mobile you have GPU hardware, like a graphic processing unit is there, GPU. Okay, so if you use this GPU, you can save little more power, so it is energy efficient. Of course, same video codec, same operation can be done with the CPU or GPU. So CPU is more power intensive, and but this GPU is more energy efficient. So that's why we can have the difference, like acceleration required. And this kind of 8K resolution, you need multiple or some decoding. When it is decoding, you need multi cores to do partitioning that different pixels and reconstruct at the display side. Let's move on. So specialized hardwares, class of hardwares, if you are look at, so this artificial neural network, and then special, so accelerating this AI applications are ANN, also called so deep neural network, DNN. And so these are terminology like ML, DL, machine learning, deep learning, and then spike neural network, SP, SNN. So these all like a part of your total artificial AI. So this all comes interchangeably we can use. And machine learning application related, especially computer vision, image processing, and these applications we require the hardware, specialized hardware. So deep neural network extremely high competition, compute intensive, and the memory cost also be there for the deep neural network. So in deep neural network, majorly convolution methodologies or algorithms, and also matrix multipliers, some kind of operations are there. So obviously, this is going to be very challenging for the hardware support, and that's the reason we need specialized accelerators. Now, the same problem statement, of course, here with the pictorial diagram, you can see the 1990s, we have PCs, and between this decade, you have 3D graphic card. You can see personal computer and small, like a low application mobiles, only limited functionality calling and all. Not video processing is not much image and video processing at this mobile at this stage. Then when you see the mobile evolution comes here to 2006 to 14. So smart mobiles came. Smart mobiles, so many functions are there. And then you have the video, audio, and also surveillance applications and all. So it's like a driving factor. What are the driving factor for our AI accelerators? It is going to be PCs to mobile, smart home, or smart watches, smart healthcare, so smart factories. So there are everywhere that wherever you have enhanced intelligence required. So robotics nowadays, human robotics are coming. So and now automobiles also. Earlier, only dozens of chips required in a car. Now presently, minimum 200 to 300 chips required. So it's like a, and you need some kind of like a different EPU, engine processing in it, or something like a separate MCUs are there. So different functionalities and all. So human augmentation, something like at the between means 2030 next decades. So it is going to be something, it's human plus intelligence going to be work collaboratively. So human all are like so you can see the sensors are play. And the best example, like a smart glasses nowadays, it also read in front of you data, and it process and it help you, and also audio processing, video processing, everything is there. So robotics also, now presently robotics become like a human kind of natural language processing, and it is talk communicate naturally as a human being. So these are the driving factors for specialized hardware. And then problem like a model expansion, like I can see this one, performance AI models like AlexNet and Elo. So these are the models. And now presently chat GPT 4 or 5, right now presently. So every time when we are communicating with the chat GPT, so we have been uh, like using AI accelerators in the data center somewhere. Let's say I open my chat GPT, I ask some audio, and that will go to the cloud, and it processes and within less latency, and it is going to be reply back. So we have Moore's law, right? It's like 18 months, but in the data, especially AI models, and AI models are doubling every 3.5 months. That's why there are mushrooms of AI startups are coming, and they are using different models to train. So we have so many Gen AI engines like Chat GPT, there DeepSeek, and then now presently Perplexity. So these all you maybe experience different way. Like some of relevant answers, some models are good and some models are reasoning good. So like a DeepSeek, if you ask, it will give reason why you are means some equation. What is the background about reasoning way? Some models are, there's no much reasoning, it straightforward answers it will give. So it's like a month, different models are. And the flops is, we can call it as a computing power. So floating point per second. So this one is a unit for your AI competition or the models competitions. So it's creating continuous demand, and it's a continuously been the trend. If you see, you can from the way models are increases and the competitions also increasing, and for, to reach the performance. Now, if you see the accelerators, so general purpose GPUs, so the advantage, fast competition happens, and it's nowadays like a trillions operation, like a, you know, for a simple operations now presently, trillion or trillions, 10 power or some exa per a second. How many number of operations happens for a AI related one small models? 10 power 15 times. So that kind of like a requirement for the computations, for the operations to be executed. So it's like a, we required not a parallel processing. It's required massively, and you need some kind of like a simple example. If you take some of the cores, NVIDIA kind of H100, they have 6,000 cores are there. So that do the multiple parallel processing, not multiple. It's a massive parallel processing. Other hand, if you take AMDs, and they have their 60 to 70 cores there in their uh, core. So some of the chips are, they have been enhancing with the multiple threading, multiple cores. So I will come to the tools. When you do the EDA tool, RTL to GDS to flow, you can use parallel processing for your tasks, like a placement, routing, and all. And then some hardware, sometimes the hardware in the chip memory, on chip memory, off chip memory, there are two ways we can be realize our designs and all. So off chip memory means if you need high bandwidth memory. HBMs are the new technology, and all the companies are, they have been the best example. If you see in the news, current news, Microsemi and all, they have the lot of projects on HBM. So they have been doing specialized hardware for the AI related data centers and all, because the training, and then it is deploying. So AI accelerator, best example, cloud and edge devices, edge AI. So edge is nothing but, if I, my mobile is edge AI, so if I say it will answer, it will delivered here, but it happens in the cloud. Cloud is, it will read your I mean it will train your data, and then result it will be display in the edge devices. So the key assessment, other parameters like processing speed. So we need to be without much means a delay, and faster with less latency and all. And autonomous vehicles. So autonomous vehicles, you need immediately process your camera data process, and it has to take action because it's a life and kind of questions. And also, it critical applications, you need this kind of processing speed. So means gigahertz nowadays, 4 5 gigahertz, and if you have more 10 power 15 kind of speed also be they require to process the operations. And power requirement, power consumption always be, you need a low power techniques, architectural level also, design and development, and everywhere, every stage, a part of design cycle, or life cycle of your design development. And size, obviously, so like a small portable devices, you required a smaller size. Mobile, so the best example, like you need same kind of applications, audio means something like autonomous vehicles, you may go for 90 nanometer or 180 nanometer technology node. But if you go for mobile, you need minimum 7 nanometer or 5 nanometer, all the mobile devices nowadays. So this means like a size is depends upon the chip sizes, depends upon the application. So when we are also think that, like when I want to do research, some reference papers how they gone for lower technology node. So it's based on their applications they have implemented. But if I'm targeting for even some of the 180 nanometer also still relevant nowadays, some of the applications, they can, what we call it as a legacy nodes, technology nodes, 90, 180. So these are technology nodes, we can also go for some of the applications. Total cost is like obviously NRE cost. So especially AI related accelerators use NRE cost because there need to be a lot of data. So all we can see majorly now present technology running on the two wheels. One is the data, another one is the computation. So huge data is there, sharding loss, the huge data AI related algorithms does, and the compute engine. So the compute engine, we require the low power, high performance, and then means the time to market. So compute. So now we are AI accelerator come to the part of this compute engine, of course. Yeah, so now some of the architectures, if you are observed here, so this is see data stream and then instruction sets. Okay, so initially, so SISD, so single instruction, single data. So this one, so it's like a uniprocessors. So when you go for single instruction multiple, so this one is like a multiple uh, single instruction and multiple devices. So you can see this one. So multiple data here, multiple data, single instruction. When you go for multiple instruction, single data, and here this one is MIMD. So multiple computers and multiple. So this is called multi-core, multi-threading. So you can see this advantage of single core and multi, and people AI related are, so this is the approach they have been using, multiple instruction, multiple data. So just if you see here, normal general purpose processors are CPU and then GPUs. So GPUs are a kind of like a CPUs, several CPUs all and then different vector processing. Okay, so but in CPUs, single scholar processing. When specialized processors are there, FPGAs are well known. FPGAs are like a we are all aware, right? A part of our academic, everybody we are all been using the FPGAs. You can reprogrammable and reconfigurable, and also partial reconfigurable. Some portion of your chip can be do for some operation, other portion also be done. And also FPGAs are very some of the operations means many of the AI accelerators, they have been ending with the AI FPGA based, because that it's a the power consumption is, of course, speed and power is not very up to like a 6, but reconfigurability and flexibility, scalability, that's a good in the FPGA's domain. So that's why the best example, if you see here, a simple ALU kind of algorithms, you can go a simple FPGAs and all. But if you go huge kind of like a floating point unit, which is required more in loop, means nested loops, all the kind of like a more intensive, more number of logic are there, and so critical or crucial logics and all, we can go for like a, the power related things are, when you want to go for optimized power and all, ASICs is the best. So you can see, so you can correlate that way, or some extent, of course, nowadays FPGA is also very powerful, and it is now the difference between ASIC and FPGA is very small nowadays, and the FPGA is also huge. LUTs are there, you can map bigger designs also. But some extent means performance wise the best, because we have been design ASICs from the scratch, means a kind of like each and every stage we have in our control. So that's why it's like a optimization is more, and PP end of the day we have to correlate all this architecture with the PPA, and other things are time, turnaround time also, PPAT. So these are the factors. So these are the legacy terminology and the market-wise turnaround time. If a development cycle is more turnaround time, and by the time other vendors, I mean the other already be exist. So this is a four parameters are very important when we are choosing for architecturally. So NPUs are the best example, like a M4 processor, new NPUs are there, mobile processing, and new. It's like a human brain kind of mimic the designs and all, and it takes the within nanoseconds of operations and all. You can get it milliseconds of results and all. Okay, so emerging technologies like a processing in memory. We'll see each architecture in detail subsequent slides. Yeah. Now, the architecture diagram, if you see here, some of the example of companies and also to give the glimpse of the companies. So here, so as to general purpose processor like CPUs and GPUs. So CPUs are wise, AMD, Ryzen, and you can see the Intel i5, i7 processors, 11th grade and all. So then GPUs wise, the NVIDIA GeForce, and then AMD Radeon, so RX 67. So these are the two best example for GPUs. When you come to the special purpose processors, and FPGAs are Intel Stratix, and also be there like Xilinx Zinc processor, and also ultra scale. There are many advanced FPGAs from the Xilinx also. Now, the fixed point, like a fixed logic, like a Google TPU, Tensor Processing Unit, and the Habana, Intel, Nirvana systems. So these are the application specific AI accelerator hardware. So when you come to the emerging, like the one more NPU wise, so it's like a Exynos, some Qualcomm's Hexagon. So this is a Samsung. It's a Snapdragon was there. Qualcomm's likewise the mobile processor. So emerging technologies like you can see processing in memory. So here memory and processing is in the one single silicon. Earlier, like a Van Neumann architecture, you have computing core logic in other hand, and the memory is accessing read and write in other part. So, but it is processing in the same memory, same computing process, same in the one place. Neuromorphic computing is one of the advanced emerging trends, and quantum computing, AI, wafer chips, and analog-based memory technologies is the emerging. These are the emerging trends. So when you come to the CPUs, so as I said, it's like all are like, so there are two CPUs here, and you can be communicate with the bus interface, and you can see generic dual core. And when you core dual core and dual processors, so so it's core and single core, and you have the multi-threading. So see these are four cores, total four cores, and two CPUs, four cores, and then different threading. So these are the generic dual core processor and all. So this we can see normally. Just I'll take you to the tool flow to see this. Before that, just like these processors are most personal computers and all, and the tools and the serial processing. And if you limited number of parallel tasks, multi-cores, so this is a multi-cores, and powerful general purpose, it can support for high number of simultaneous tasks, okay, that is required for neural networks. And the temporal architectures like single instruction multiple data is there with the centralized ALU. So let me take to the one example, the tools. When you are working with the tools, it's come out of yeah. I'm accessing my tools here. Yeah, ma'am, could you please confirm? I've been sharing other window.
Yes, sir.
Yeah, you could able to see, right? Means a
Yes,
browser.
sir.
I connected
Yes,
with
sir.
the browser. Yeah.
Yes, sir. Yes, sir.
So, yeah, thank you, ma'am. So here I'm connecting cloud-based tools where my EDA tools are there. So cloud is Azure here, Microsoft Azure. So there my tools are there. So now you just if a simple RTL to GDS to flow in this kind of, especially for physical design, in the physical design, uh, and also parallel, but other tools also be there. But I just want to give you the demo of means the Innovos tools, how it is going to run your design in a multi-core multi-threading. So when I open my Innovos tools, you can see here 8 CPU jobs are allowed with the license. The present license is supporting 8 CPUs. So that means here there is a just a few either slides we have seen right here. So the CPU two CPUs are here, whereas here four CPUs are there. Here four CPUs, and
ఎట్లా
there is
అనేది
two CPUs. I request some of the participants, please turn off your. Please cross check. Okay, yeah. So if you see here, and the same way, the same here for two. My tools, when I want to be access my tools here in the cloud, the tool invoking time, it's showing that eight CPUs are there, and it is allowed eight. So the design, when your bigger design, let's say like my design is a uh, some like a complex addition or some uh, at least you can say eight floating point units, eight FPUs. You can think like, okay, eight floating point unit. Each and every core handle one of the FPU floating point unit. So the design is partition. The EDA tools here, uh, it is partition for automation, and it is automatically considered like, of course, a design architecture level also you can partition as a team member. Each team member can handle one FPU floating point unit, and top level means integrating all eight FPUs. And the tool wise also, when you are implementing implementation, digital implementation, from especially from synthesis to GDS to file, some of the tasks like placement and routing. So here, these are the tasks you required some multi-core and multiple processing. So this one is like a placement here, and then routing. So especially these two stages, your tool will says that whether you want to go for your multiple CPUs or not. So just load. Let me load one small design to see that option. So now I'm importing a design, a small counter program to show you that option. But if without any of this design, it not show that option. Actually, if I'm not load any of the design, this one is a disable mode. So you can see placement disable. So to enable this two CPU multi-core option, so I'm just adding some design, one demo design here. So netlist file, I added one simple counter, and then so I'm not showing here the design complexity. So the tool advantage, the multi-core multi-threading advantage, uh, I want to demonstrate you. So this is the left files to give here. um, of course we you all aware of this, but the options you maybe not observe these options. That's the reason I'm just bring your notice. So next one. So here power, let's give for VDD and VSS, and then counter view files. Okay, this has some. So my design is loaded. Once the design is loaded, now at the floor plan wise, so uh, floor plan specify floor plan. I can go. This is a one, and this one point 70% for logic, and this for 8 macro space. Let's create my logic here. Okay, and then when you go for power plan, okay, next power plan also, let's create one ring. And metal layers, top metal layers for power related ring, and then default values of 1.8 is fine. So it is created. Then now the step we came here for our placement. Okay, So if I zoom in, something is there overlay. Yeah. So now let's go for place the standard cells. So standard cells like a run placement floor plan mode. So I can go for here full placement, and now you can see number of CPUs. I can go this as my tool said eight CPUs. Is you can click on this. If I mention this one, you will get the different runtime. If I go for single CPU, it may give it may take 100 milliseconds. And if you go for 8 here, it will decrease drastically 8 times. So it may be even 10 milliseconds. Within 10 milliseconds, entire your placement is going to be complete. Okay, so let's go for this one, and then so 8 CPUs, and then run full placement. Just click on it. And then runtime also we can see in the terminal. The difference of the runtime also you can see. CPU runtime is this much, and real runtime and memory usage and all. And you can see the with one CPU, and of course this is even not means it's a second 1 second it's showing the round, but it's happens in milliseconds or even less than that. Small designs, zero point zero 0.01 second. You can see the global runtime 0.01 second. So if we go for one CPU, it may not this value. Okay, let's do that. Of course, I'll go again. So this is the eighth one, right? Let me do the same operation with the single core. Specify again one placement with the with the one one CPU, and then rerun. Now you can see yeah, so you can see the overall runtime 0.00, and if you go a little up, yeah, CPU real time, so you can see this one 0.002. So you have the difference. You can see the difference of 39.9, 39.6, whereas that one is very less time. It has taken more time. One CPU has taken more time. So here we can see the even it is not captured in this. Okay, so that is like a difference is like the tool has intelligently idiot tool has based on your bigger design. We are not observing maybe small designs, we may not notice this one. And if you go for a kind of like a complex SoC, you need these options: multi-thread, multi-core optimization, means placement and routing stage also. If you go for route design, so here also the sometimes it will go days routing and placement for a real-time projects. So you can also CPU single CPU or 8 core CPU, and I can't go for behind 8 core. The reason here in the terminal already, when I'm invoking my tool, license is support only 8 cores. So you can see this one. um, 8 CPUs are allowed for this current license. Okay, so but if I have my hardware, if my system is more than 8 CPUs and all, maybe that hardware infrastructure based also, it will your license will support. Okay, licenses and all. So this is how we can see this CPUs and multi-threading. Let me come to here. Yeah, now GPUs, when you come to GPUs, it's like a work horses, like you have parallel threading or parallel works. So the best you can see representation here. See, this is a 4 core, each core independently work, and of course, it has each and every task should independently. There is a condition for this to handle this course. you need a different task independently has to be, no interdependent. If you are dependent on each and every task, we have to be aligned that. So that is a of course that is a high level alignment for that. So when you come to the CPUs here, see, one processor you have 32 cores are there. So this kind here, there are four in the CPU, four cores, but here itself you can see at one CPU itself 32 CPU cores are there. And likewise, multi four multi processors MPUs are there 32, and this kind of things are stacked like a here 14, and this side also means total is that 14 micro multiprocessors, multiple processors. Okay, each contain 32 cores. So that means it's a huge tasks it can handle, whereas the four cores. So it originated to accelerate and parallel computing purpose, and the approach is slightly effective for complex deep learning algorithms. And it's like each and every processor are taking consider data simultaneously, and this is useful for machine learning, video editing, and gaming. The best example, something like if you have in your laptop GPU 2 GB, 4 GB, when you are editing, video editors especially, they can see the fastness and all. So if you don't have GPUs or that in your systems, normal laptops and all, so you will not able to edit your video high resolution. It takes a lot time to be frame by frame and all. Okay. They can see video editors are very well aware about the advantage of normal CPU to GPUs. So current workhorses for DNN training interface. So one of our team member, they published some of the paper on this acceleration of, we can call it as a parallel, massive parallel processing in this parallel workhouse. So one of the paper I'll show, like to show you. So first initially creating one core, then replicating the same core 32 times. So, okay. So he was my manager. He published some paper in the microelectronic journal. You can see this. So it's a high throughput, targeting for high throughput. That's the reason he massively parallelizing. And also this is the operation. Binarization is the operation for 8K resolution, 8K and above resolution video processing purpose. And if you see here, especially at this place, in the video coding, at this place, high throughput, because different directions data is coming, and you need encoder at this space, and that too multi cores required, not a single core can't handle, so multiple cores. And the single core engine is here. So if you algorithm wise is here. So in this entire this is the binarization stage. Other stages are there. Binarization, in the binarization is these are the operations in the binarization. Okay, so a single binarization core is this one. In this single binarization core, unary, truncated unary, fixed length, truncated binary. So these are the hexagon. So these are the operations, mathematical small operations, and with the controller, and it will be execute your syntaxes, or we can call it pixel data. So when you go down the side here, this block they implemented in the hardware wise. So this kind of high resolution frames, each and every block 4x4 is processing by different binarization. So the different binarization is processing to. So actually this one is the one unit. We have seen single core. Okay, you can see this single core binarization unit. So in the single core, the operations are there. So you can unary, truncated unary, fixed length, hexagonal, and truncated binary. All those operations are in the single core. So this single core replicated with the few 6 times, you can see here. Single core, they have called as here 5 different cores. You can see. So binarization 5 times replicated. So this one is 5 core. So this is 5 times is running here, and you need data processing to handle that input side, output side. Of course, here serial in, parallel out, and parallel in, parallel out, and the data. So here acceleration is happening with the 5 different cores and parallel, massively paralleling here. And if you go high level image for this design, yeah, each and every, yeah, this one is the exact, like the cores, all 5 cores are each and every core independently, and the syntaxes, 5 different syntaxes at once it is going to be executing. And timing diagram, if you see, you will understand how it is optimized. And so this is the dotted lines are 5 cores. You can see 5 core binarization happening this. Okay. Yeah. So um now if you little go timing diagram, you will understand. Yeah, there is a conventional. So if you see, um like this one is your clock going. So your five s- elements, 5 syntax elements are processing at each and every clock cycle. So this is the parallel threading. A parallel 5 cores are handling 5 signals. So this one is data input is coming and preparing this data to give each and every core. So you can see this each and every core is distributing happening this one. Okay. So this course immediately then after 5 latency. So this is the latency, of course. Initially, uh, 5 clock cycle latency. Later, you have continuous through output is coming. You can see each and every clock cycle your data executing. So these operations, and here output side with the one more clock cycle, and one total 6 clock cycle from input to output. Input to output, there's a huge means entire binarization is happening. But in this is a parallel processing timing diagram. But if you compare to conventional, yeah, here it is the advantage of this parallel processing. So if you see here, single core, if I go single core, I need to process each and every clock cycle. There is a syntax element one by one simultaneously, like a one after other, sorry, one after other. So the it will take, this will execute in the next clock cycle like this. So same five syntax element, you required 9 clock cycles, 9 clock cycles for single core. Whereas 5 core syntax, I mean, so binarization within 3 clock cycles. So we can see this is the 3 clock cycles. So we saved almost 6 clock cycles. So within this is the input clock cycle and output clock cycle. So next clock cycle immediately your data. So conventional required 9 clock cycle, whereas a 5 core required 3 clock cycle. So we saved 6 clock cycles data. Means, I mean, 6 clock cycle. Each clock means clocking, triggering clock means you are saving power, and also throw output is more, and you can have this kind of multi processing. It's called massively parallel processing architecture. So architecturally level, we can enhance the likewise. So you can, this kind of things are NVIDIA and all, they do the multi core. That's what 6,000 different cores are working together. Well, this is regarding, yeah. So now, cpu gpu comparison. So if you see this peak and performance wise, CPUs are exponentially performance giga floating points per second, where CPUs are not up to mark compared to the in 2020 years. You can see 2020 years GPUs are dominating than CPUs. Okay. Yeah, core count wise, high-end CPUs are AMD Ryzen might have 64 cores, whereas high-end NVIDIA A10 have 6,000, around 7,000 cores. See how much difference, lot of difference, right? Even not even near. So 10, I mean, so, 6,000 times. Performance wise, GPUs are demonstrate significantly higher peak bandwidth and power gap. So architectural level also, you mean performance we get it, but ultimately still architectural level and then power performance also we need to be care, and that's why GPUs are more in demand at present AI, and you need because more multi-threading, more cores can handle, so that more data sets are there. So each and every data sets will have the massive data sets are there, right? So you need to train that hardware and to give, so you need more cores. There's a GPU is the best suitable for your AI applications. Now, this one is a more elaborated way with the names. So CPU side, min and maximum core. So Intel i7 10th generation 19 to 19, you can see this 8 maximum CPU cores, and then 4 is the minimum for Intel, and AMD 16 is there, almost double of your means Intel to AMD. And then Intel Core have the i9 and 10th generation 2020, they have all the way 8 to 28 maximum, and then Xeon processor 28, and Intel again 56 is there. AMD Ryzen, so AMD Ryzen 16 to 64 cores. Okay, so over the period, so you can see initially was 4 cores to 2019. Within means in the same year, almost 1 or 2 years, they have realized a multi-core, multi architectures and all. Number of cores are significantly increased 6 times 6 months. So GPS wise, initially 2014, that time just evaluated AI related task, and 20s around 20. So now Nvidia that time they released this one. Of course, this 800. Of course now B, and there are so series are there. So a lot of architecturally come something like also chiplet kind of architectures and all. There have been stacked CPUs or stacked cores are there. So this is the difference of comparison in the cores, GPU versus CPU. Other hand, now after GPU, now we have FPGA related architecture. So FPGAs are array of the CLBs, right? In the connected with the interconnection with this network means matrix. So ALU, arithmetic logic processing chain, and then configurable logics, array of the configurable logic. Like initially, what we said here, like a DSP 15 is the specialized architecture for multiplayers that will give you better results. And there is a Mac DSP application purpose, Mac blocks, multiplier and accumulator. So with this, you will get the better results like a specialized hardware. Same way. So we have some extend some low to medium AI related. So we can use this AI, FPGA architectures. So Vortex family from the Xilinx, and then Ultra Scale, and the Zinc processor with the uh, ARM processor plus as well as the FPGA domain. Both are there stacked. ISIS parallel programmable logic and programmable system. With that, you can also have the both like training you can do in the programmable system, like a processor, ARM processor, a dual core ARM processor. Um, Cortex dual processor, and FPGAs wise, you can have 7 series FPGAs, advanced or ultra scale FPGAs. Hopefully you are well aware, because many of the our universities, Indian universities, we have been using a part of curriculum in this all FPGA architectures. ASIC architectures for DNN, especially DNN applications, you can see off-chip memory, and then you need HBM or interconnections for gigabytes per second, and network on chip, and PE arrays. So each and PE array is a specialized hardware implemented on ASIC and FPGA. So DRAMs, so DRAMs, several DRAMs, and global buffers are GP network and processing elements. So processing is actually hardware processing, actual logic register files and all. So this will, it's a custom build for AI applications. So many of the companies, yeah, are we going to see the name of the companies who work for this ASIC architecture for DNN in the next slide? So neural processing unit, NPU. So this is one PU, one processing element, single processing element. The single processing element, if you arrange like this, eight different, and you have FIFO, first in first out, and then scheduling buffer. Like earlier our paper, we used SIPO and PIPO, serial input and parallel output. They have used here parallel, first in first out. So with this bus architectures, communicating bus architecture, eight Ps we can use for this NPU, and this one is more, and one PE can do this MAC unit. Here is the MAC unit. These two logic are called MAC, multiplier and accumulator unit, and then input register, output registers, communications now. So this is majorly used for CNNs, convolution neural network purpose, and multiple computing and pooling required, increasing of performance. Some of the examples like a Qualcomm Hexagon and Exynos of the from the Samsung. So these are the NPUs you can see in the Apple M4, M5 chip, and those who have been, and also some APUs are there. The Android companies AI processing unit also be they use as this mobile and edge devices. Okay. Now, the deployment, like where we can have this AI accelerators, cloud and edge. Okay, so the best example, this cloud-based tools I have invoked, right? So these are the cloud-based my EDA tools. I've been without any latency, much latency. The same like the tools are not installed here. Same like, okay, I've been accessing from there. Need to be. So it's like a my tools are given space in the cloud, Azure. So we install the tools. So I'm just real time. So same like in the local system, what are the tools are the same way it behaves. So without latency and all, cloud is happening and all. Edge devices is mobile. If I processing this results of cloud in the edge, that is like you can see the difference here between these two terminology. Cloud is the servers or data centers. You can see cloud centers, and the data is learning, and model is happening here. Data and learning model happen in the cloud. So then it is control and model signals will give to the edge terminals, like edge the CCTV cameras, and then desktop or laptop, and also mobile, like this smart glasses, and then drones and smart mobile applications and all. So here it is communicating. You can see this is the data is going this way, the light blue color, and red signals is, it's like a decision inference, like a decision is happening at this stage. Okay, so this is the edge terminals and cloud services here. So generative AI is the used for learning and training there, and computing high power required. So the best example, like a model set and trained and large data sets, you have used data sets to be trained. Nvidia's Volta and Google's TPU is the example for the cloud and server based. And then device edge, the specific AI inference. So running this one, specific AI, low power, low latency, and real time operation. So the some of the examples of edge devices: IoT, wearable devices, smart wearable, and portable devices, smartphones, and automotive applications and all. And here there's a very good, I mean, sir, pictorial representation of voice assistant. Let's say like a voice you have used like a Siri or kind of interface. You have given the question and it is gone here, cloud and server. So in the cloud and server, the data you have the learning and pre-trained network is here. And then interference here, the decision that the results will come and output is, you can see this voice results here, assistant. So the edge and cloud work in hand. So like inputs and out, like the data, everything is processing, training and all in the cloud, and then output, input taking at the edge devices. The challenges are almost we are flag end of our discussions. Few more slides, 1 or 2 slides. So now the discussion challenges, if you see architecture wise. So architecture like a AI processor architectures and memory is separate. You need bus interface and read and write latency and all. So this is the Van Neumann architecture. So tremendous like this is where companies, many of the companies like working on called HBM, um, high bandwidth memory accessing. With this, they have been serving many of the solutions and all. Okay, let's see that how it is. Some of them. So solution one HBM. So you can see the stacked D memories dice are here, and it is communicating network with the TSV through silicon vias, TSVs. So you can see these are the through silicon vias and connected, and it is a package substrate down here. And downside you can see interposer is the connector, like a logic die and the physical layer here, and it is communicating with the SoC or GPU or CPU, whichever. So this is different, all the way different architecture for memory solutions. Now here it is directly, and it is a less latency and all. So it's a stacked memories are there, DRAMs and all, and it will increase the like memory increase the bandwidth 1024 gigabytes per seconds, versus earlier it was the 384 gigabytes, the small footprint of hardware. So HBMs are solving earlier conventional vans Neumann architectures related. Now many of the best known for the HBM solutions, companies like Microsemi and all, they have been working with the AI supported HBMs. So next one is a solution for this one, in process instead of memory, off chip memory. So you can be keep in the same core memory and logic in the same within. See here, there's 3 cross 3. So each non-Van Neumann architecture. This one. So memory process in memory, so opposite to the Van Neumann architecture, and it, logic and memory is the same and performs directly inside the memory. So it reduces the data movement of read and write operations and higher bandwidth, extremely energy efficient. And it is often analog processing and sensitive circuit devices it solves. So that's some of the challenging when you are working with this in memory. So here the difference between the conventional and processing in memory, that same. So you can conventional. So you have memory activation and your weighted memory. So bandwidth is compute Mac unit here. But if you see input activation and you have the converters, data converters from input to output, and both are memory and weight are in the same one place. So this is more good architecture. Okay. Finally, this future going to be with the AI accelerators going to be majorly in the norm, neuromorphic computing. So here neuromorphic computing architectures is like a mimic of our brain, neurons and synapses. So People are thinking like, why we need to work with the electrons, why not neurons? So that way the research is going. And with this you can have like a brain have trillions and trillions of neural network, right? So it's like creating that kind of is very challenging, of course, but it's a small step by step research oriented, and they have been going and spiking neural network, it is called ssn bin. And it is incorporating there's no like a earlier means in the present electrons are clock kind of concept, but it's asynchronous. So no clock concept. And integrate and fire, it's like a spike, one spike and all. So brain functions like a plasticity learning and directly communicating. So it's just like a on the go, it's learning and without any much like we have to be do like a cloud and edge process and all not required. So some kind of like a one chip itself, it's a all in build some and many things it can be handled at, even now presently in the companies, means many of the companies working on this. So some of them are releasing there, and but it is yet to be established as a concept. Computing is more intensive, and they have been trying to be finding and if it is succeed, and a lot of and the same way like a quantum computing also, instead of binary zeros and ones, so they have been qubits. With that qubits can also be more compute intensive, especially drug discovery. Some drugs are required more and years of that equations combinations and all, it's a simulation required. So that kind of applications qubit means quantum computing simulations are within minutes or seconds, or you will get the results when you compute. At present it will taking days and months for the drug discovery combinations. So that are the some of the applications people have been deploying. With this, I hope as best, I mean, so we covered all the what we have discussed in the introduction and all. So yeah, so thank you all for your attention and time. Now the floor is open for question and answer. I'll try my level best. Yes, ma'am, over to you. Thank you. I hope we are
Uh,
in the time.
yes, sir. Yes, sir. Yes, sir. Participants, if you have any doubt, you can unmute your mic and you can ask, or you can post it in the chat box too.
Good afternoon, sir.
Yeah, good
Sir,
afternoon.
I have a query. You mentioned the term DLL, Delilog loop. So I want to ask you now in AI accelerators, which kind of DLL is more suitable, like all digital DLL or mixed signal design DLL?
Yeah, of course. Your question is very, technology specialist. They can answer, but as my experience, it's now presently digital wise very well matured, man. So at present very matured. So, but if you have analog part of mixed signal, complexity is increases, but it's not a doable. Not saying it's a doable at present digital wise. But if you go for mixed type, its complexity increases, and to establish your algorithm to be work, it's a huge cumbersome task for verification point of view. Design point of view we can do that, but verification point of view, how we can verify with the analog environment or mixed signal environment, but digital we can do that. Yeah, I hope I partially answered your question.
Yes, sir. Yes, sir. And my another question is that you showed some cloud-based EDA tools. So, is it, can a single user can access these tools on paid basis, or is it is institutional based?
Yeah, yeah, you can access. We have deployed. Hope you are still seeing my screen. uh, am I closed this one? Could you able to see my screen, ma'am? I'll just opening.
No, sir.
Okay, let me reshare. Yeah, I'll show you place, ma'am, where our company also give this cloud-based tool access for the those who are interested in. So we have training division name called Abhyanta. Okay, so in Abhyanta, I can see VLSI. Yeah, EDA tool access. Yeah, you can get request from here. Our team will help you. So you have to send the request hourly based. You can access our tools like this. The same tools what I have been using browser based actually. So we have buy some space in the Azure cloud based. There we tool install. We are hosting it's a training licenses. So as you all know, Entuple is a official Cadence distributor, EDA tool distributor and training partners. That's the reason we are hosting the tools in the cloud, so you can accessible with this.
Sir, so
I,
it's cost wise, is it affordable for a single user?
yeah, it's only hundreds. Means I'm not sure exactly the number, but it's a bare means it's like yeah affordable, madam. As a single, you can hourly like not more than hundreds. Means I guess hourly base it's like less than 500. I guess around. You can cross check with. You can please send
Okay.
to that
Yes, sir. Yes,
email.
sir. Yes, sir, I will go through that. Okay, thank you very much, sir.
Welcome. Madam.
Thank you so much, sir, for accepting our invitation and sharing your expertise among us. Now I invite Sendil Priya to deliver the out of session. Thanks for the session 11. Over to Priya.
So, good evening, everyone. On behalf of R.M.D. Engineering College and Department of Communication Engineering, I express gratitude to our experts person, Executive at Digital Technology Bank, for delivering such an enlightening session, where your valuable insights have provided the participants with great inspiration and technical clarity. We truly appreciate the time and effort you have taken to share your rich industry experience with us today. Thank you for a wonderful session and being part of our FDP today. Thank you.
Yeah, thank you, ma'am. Thank you so much for your, the great this kind of hotel FDP, and I wish you all the best for remaining part of the program. Thank you once again for the opportunity for us. Yeah, over to
Thank you.
you. Ma'am. Thank you.
Thank you
Thank you
so
all
much.
participants, and yeah, have a good day all.